In previous videos, we have looked at the dot product, which is a way of multiplying two vectors to get a scalar. In this video, we will look at the cross product, which is a different way of multiplying two vectors, and the result of the cross product of two vectors is another vector. We will look at the magnitude of this vector as well as its direction. If you know the components of the two vectors a and b, then this expression gives you, in component form or unit vector notation, the expression for the cross product of a and b. Now, this looks fairly complicated. So let's look at an easier way of writing that expression, or at least of remembering it. One way is to simply rewrite it by moving the unit vectors to the front. Why does that make it easier? Well, let's look at the first term. That is I hat ay bz. We know that I hat is associated with the x-axis, and so we see a pattern x, y, z. What about this term? We leave the I hat alone, but switch the subscripts on the other two terms. AYBZ has now become AZBY, and we stick a minus in between. Let's look at this term. This goes YZX. And again, for this, we leave the J hat alone and switch the Z and X to get AXBZ, and we stick a minus sign in between. And similarly for this term. So what is the pattern? We see the pattern that in the first term we have XYZ, XYZ. In this term we have YZX. And in this term we have ZXY. So, in each of these groups, we start with going around the circle. So we have XYZ, the next one is YZX, and the third one is ZXY. And then for the remaining three terms, we simply switch the subscripts on these two. This is one way to remember the expression for the cross product. If you know how to do a determinant, however, this is a much simpler way to do the cross product. If you are doing the cross product of A and B in that order, so A cross B, you take the determinant of the following matrix. In the first row, you write I hat, J hat, K hat. In the second row, you write the components of the first vector, so AX, AY, AZ. And in the final row, you write the components of the last vector, BX, BY, BZ. Evaluating this determinant gives the same expression. If you do not know how to do a determinant, ask me, and I will show you a couple of different ways. What is I cross J? Here are some options. Pause the video a moment and try and remember, or try and calculate. The next slide shows the answer, and the answer is I cross J is equal to K. If we look at other combinations, we see I cross J is equal to K, J cross K is equal to I, K cross I is equal to J. Unlike the dot product, where A dot B was equal to B dot A, in the cross product the order matters, and so I cross J is not the same as J cross I. In fact, it's the opposite, or the negative. So I cross J is K, but J cross I is minus K, k cross j is minus I, and I cross k is minus j. What about the other products, such as I cross I, j cross j, and k cross k? Those three are 0. How do we remember these products? We can remember them using a simple trick, ijk, ijk. I cross j is k, j cross k is I, k cross I is j, and so on. That gives us these three relations. And now if we go in the reverse direction, we pick up a minus sign. So j cross I is minus k, I cross k is minus j, and k cross j is minus I. Also, by noting that we never see two i's together or two j's together here, we can say that I cross I is 0, j cross j is 0, and k cross k is 0. Remember though, this trick only works for the cross product. There is a simple way to visualize the magnitude of the cross product. First, let's look at the algebraic expression. The magnitude of A cross B is given by the magnitude of A times the magnitude of B times the magnitude of the sine of the angle between them. Notice how this is very similar to the dot product, but instead of a cosine, we have a sine. This tells us that if A and B have an angle 0 between them, then sine of 0 is 0 and the cross product is 0. Or if A and B have an angle of 180 degrees between them, again sine of 180 degrees is 0 and the cross product is 0. This expression has a very nice geometrical meaning. If we are given two vectors A and B, we can use them to complete a parallelogram. The area of that parallelogram, this red shaded area, is given by this expression. In other words, given two vectors A and B, you can think of the area of the parallelogram that they form as being the magnitude of the cross product. Once we have this way of visualizing the cross product, it is easy to remember that if A and B are parallel, the cross product is 0. Why? If A and B are parallel, they look like this. As you can see, there is no area enclosed. In fact, there is no parallelogram, there is only a straight line. Similarly, if A and B point in opposite directions, there is no area enclosed by the parallelogram. And so the area is 0, and so the cross product is 0. Once again, when is A cross B 0? It is 0 when the area of the parallelogram goes to 0, which will happen when A and B are parallel. Another way of looking at it is to ask, when is the determinant 0? If you remember the properties of determinants, you know that if any row is a multiple of some other row, then the determinant is 0. For example, supposing we have bx is equal to 3ax, by is equal to 3ay, and bz is equal to 3az, so that this row is just 3 times this row. In such a case, A and B are parallel, and also the determinant is 0. Once again, if the two vectors whose cross product is being taken are parallel, the cross product is 0. So I cross I is 0. To evaluate this cross product, You could simply multiply it out and add up the various terms and get the final answer. But in this case, it is much simpler to note that this vector is simply 4 times this vector. 3 times 4 is 12, 4 times 4 is 16, 5 times 4 is 20. So this vector is simply 4 times this vector. As a result, they are parallel and their cross product is 0. So we see that if A and B are parallel, their cross product is 0. When drawing two parallel vectors, keep one point in mind. A common mistake when drawing two parallel vectors is to draw them like this if they start from the same spot. However, this is wrong because it implies that there is an angle, a small angle, but still an angle between the two vectors, which would not be the case if they were parallel. The correct way to draw two parallel vectors that start from the same spot is to draw a single line and put two arrowheads. After that, you place the labels of the vectors next to the arrowheads. In this way, it is clear that there is no angle, or the angle is 0, between the two vectors. Vector A extends from here to here. Vector B extends from here to here, all the way. We have talked about the magnitude of the cross product, but we know that the result of a cross product is a vector. What about the direction of this new vector? The direction is given by the right-hand rule. Now, there are many different versions of the right-hand rule that all do the same thing. I will show you my version, but if you already know a different version and it's easier for you to use, go ahead and keep using it as long as it gives you the right answer. Let us use the right-hand rule to find the direction of A cross B. Let's say these are two vectors, A and B. Let us denote the cross product of A and B by the vector C. Remember, with the cross product, the order in which you multiply the vectors matters. Here we are doing A cross B. I take my right hand and hold my fingers flat and point them along the first vector, A. I then curl them towards the second vector, B. You can see that this is the angle between A and B, and so I curl my fingers through that angle. My thumb points perpendicular to my fingers, and in this case you can see that my thumb points into the board. And so we say that vector C points into the board, which is denoted by a circle with an X in it. And so we see that the direction of A cross B, in this case, is into the screen, denoted by a circle with an X in it. How do we remember which symbol shows a vector coming out of the page and which symbol denotes a vector going into the page? We think of an arrow. When an arrow comes out of the page towards you, the first thing you see is the point of the arrow. And so a vector coming out towards you is denoted by a circle with a dot where the dot represents the tip of the arrow. If a vector is heading away from you, if an arrow is heading away from you, what you see moving away are the feathers of the arrow. And so we denote this by a circle with an X. And so, once again, we see that B cross A points out of the page in this case. The magnitude of A cross B is given by magnitude of A times magnitude of B times sine of the angle between them, and then magnitude of the whole thing. Notice that this is very similar to the dot product, but instead of a cosine, we have a sine. Once again, we see that if the angle between the vectors is 0 or 180 degrees, then sine of 0 or sine of 180 degrees is 0. And so the cross product of two parallel vectors or antiparallel vectors has magnitude 0. Again, remember that reversing the order in which you do the cross product will not change the magnitude of the resulting vector because the magnitude is always positive, but it will change the direction. And so we say that A cross B is minus B cross A. The direction of A cross B is given by the right-hand rule, which is sometimes abbreviated as RHR. But even without doing the right-hand rule, we can make some statements about the direction of A cross B. If A cross B is equal to C, then we can say that C is perpendicular to B and C is perpendicular to A. In other words, the two vectors A and B lie in a plane, and A cross B is going to be perpendicular to that plane. For example, in this figure, A and B lie in the plane of the screen, and their cross product will either go into the screen or come out of the screen, depending upon whether you do A cross B or B cross A. With that in mind, try and evaluate A cross B dotted with A. Remember that A cross B will give us a vector, and then we can take the dot product of that vector with A. Think about what the result will be. To summarize, A cross B is an expression given by this determinant, and we can see that the result of this determinant will be a vector. A cross B is 0 when A is parallel or antiparallel to B. That is when the area of the parallelogram that they form is 0. And the direction of A cross B is given by the right-hand rule. We use the cross product sometimes to check if two vectors are parallel. If they are parallel, then their cross product is 0. We can also use it with the dot product to check if three vectors lie in the same plane. If we have three vectors A, B, and C, we can calculate A dot parentheses B cross C. B cross C is going to be a vector, and then A dotted with that vector will give us a scalar, which we can call V. This product is sometimes called the box product. The reason for this name is if you look at those three vectors, A, B, and C, just like we could construct a parallelogram with two vectors, we can construct a box using these three vectors. We just repeat them a few different times and construct a box. The volume of that box is given by V, that is A dot B cross C. So, if all three vectors lie in the same plane, if A, B, and C lie in the same plane, then what would be the volume of the box? If they all lie in the same plane, then the volume of the box is 0. And so A dot B cross C will be 0. We also used the cross product to construct certain physical quantities like torque, which is constructed from R and F. So tau, the symbol for torque, is given by R cross F. And angular momentum L is given by the equation L is equal to R cross P. We also use the cross product to construct a right-handed coordinate system. If you know the directions of the x-axis and the y-axis, you can find the direction of the z-axis. And that is because I cross j is equal to k. So knowing the directions of x and y, you can find the direction of z. Here's a question. If you add 3 meters I hat and 7 meters per second j hat, what is the answer? Pause the video and take a moment and think about this. The next slide shows the answer. The answer is it is not possible to add these vectors. The reason is they have different units. One has units of meters and is a length, and the other has units of meters per second and is a speed or velocity. You cannot add vectors of different units, but you can multiply vectors of different units. So even if A and B have different units, you can construct A dot B and A cross B. Finally, we end with a comparison between the dot product and cross product. First is the symbol. The symbol for the dot product is a dot between the two vectors, and the symbol for the cross product is a times symbol or cross between the two vectors. The result of a dot product of two vectors is a scalar. So the vector nature goes away and you just have a scalar. The result of the cross product is another vector. The magnitude of the dot product is given by magnitude of A times magnitude of B times cosine of the angle between them. The magnitude of the cross product is given by magnitude of A times magnitude of B times sine of the angle between them. The result of the dot product is a scalar and thus has no direction. It is only positive, negative, or 0. The result of the cross product does have a direction, and that direction is given by the right-hand rule. The result of the dot product is 0 when A is perpendicular to B. The result of the cross product is 0 when A is parallel to B. The visual representation of the dot product is the projection of one vector onto the other. The visual representation of the cross product is the area of the parallelogram whose sides are given by the two vectors. That's the end of this video. I'll see you in the next.